Welcome viewers to the third lecture for the lecture series on integral equation under NPTEL. In the second lecture, we have discussed the Leibniz rule, that is later used to convert the integral equation to ordinary differential equation, and we solved the ordinary differential equations and verified that obtained solutions also satisfies the given integral equation. Next, we have considered the detailed proof of generalized replacement lemma. This generalized replacement lemma we today again try to recall. Generalized replacement lemma. In terms of mathematical notations, this is integral from a to x, a to s n minus 1, integral a to s n minus 2, a to S2, integral a to S1, gs ds, ds1, ds2 up to ds n minus 1. This multiple integral is equal to 1 by factorial n minus 1 integral a to x, x minus s whole to the power n minus 1 gs ds. This was the generalized replacement lemma. Now, we use this generalized replacement lemma in order to convert second and higher order ordinary differential equations into Volterra integral equation of the second kind. At the first two lectures, we have seen some examples that how second or higher order linear ordinary differential equations can be converted into an integral equation. Now, in this lecture, we start with a general second order linear ordinary differential equation, which is an initial value problem. So, first we consider the ordinary differential equation that is given by d2y dx2 plus px dy dx plus qx y. This is equal to Rx. This is the given differential equation subjected to the initial condition y a equal to alpha y dot a, this is equal to beta. Now, in this equation px, qx and rx, these three functions are known functions. These three functions px, qx, rx, they are actually defined and continuous over a less than equal to x less than equal to b. Now, our target is to convert this ordinary differential equation into an integral equation, and in the process of construction of this equivalent integral equation from this ordinary differential equation, you can see that these two given initial conditions will be absorbed into the different steps of the formulation of the integral equation. So, first of all, we can rewrite this given ordinary differential equation into the form that is d dx of y dot x, this is equal to minus p x y dash x minus q x y x plus r x. As per the given conditions on p q r, this right hand side is an integrable function. So, we are actually intended to integrate both sides from the limit a to x, and since x is already involved into the equation and of course, x is the independent variable and we are going to integrate from 0 to x. So, what we can do, we can rewrite these expressions where x is replaced by s. So, this dx will comes out to be ds and then we integrate from the range s equal to a to s equal to x. So, after integration it will comes into this particular form that y dot s limit from a to x, this is equal to minus integral a to x p s y dashed s ds minus integral a to x q s y s ds plus integral a to x r s ds. Now, on the left hand side it will be y dot x minus y dot a, and y dot a is already given, this is beta. So, left hand side will be y dot x minus beta, and we can shift this beta onto the right hand side in order to get the result that dy dx, which stands for y dot x, this is equal to beta minus integral a to x p s y dot s ds minus integral a to x q s y s ds plus integral a to x r s ds. Now, we are just going to integrate this integral using the formula for integration by parts. If we integrate this integral using the formula for integration by parts, then we will be having beta minus p s y s. Actually, we are considering this y dot s as v and p as u. Limit from a to x, then it will be plus integral a to x p dashed s y s ds plus integral, sorry, this will be minus a to x q s y s ds plus integral a to x r s ds. And once you substitute this lower limit, this is a constant, and you can recall y at s equal to a, it is given, p s is a known function. So, after substituting s equal to a, this will be also a known quantity. So, you will be having this constant term, that is beta plus alpha p a, this quantity, minus p x y x plus integral a to x p dashed s minus q s, this multiplied by y s ds plus integral a to x r s ds. So, this is actually expression for dy dx equal to this one. Now, before proceeding further, I just want to draw your attention. If you look at this mathematical expression, this is also an equation in terms of the unknown y. Now, in this equation, derivative of y is involved here on the left hand side. Again, the unknown function y appears under the integral sign. So, the question is, what type of equation is it? It is actually known as integro differential equation, where in the equation derivative of y is involved, again integral of y is also involved. After few lectures, we will be discussing little bit about this integro differential equations. This is just for your information at this moment. Now, again if we integrate this result, that is dy dx equal to given by this one, then after integration from a to x within this range, we will find yx minus ya equal to alpha. We can transfer this alpha onto the right hand side to get alpha plus beta plus alpha p a, this multiplied with x minus a minus integral a to x p s y s ds plus integral a to s, sorry, this will be a to x, a to x, a to s p dot s minus q s y s ds ds 1, this plus integral a to x integral a to s 1 r s ds ds 1. Now, in last two integrals, we have to apply the generalized replacement formula. After applying generalized replacement formula, we will be having this alpha plus beta plus alpha times p a x minus a, this will remains unaltered, integral a to x p s y s ds, this will be plus integral a to x x minus s p dot s minus q s y s ds plus last integral will be integral a to x x minus s r s ds. Now, you can see first two terms, that is alpha plus beta plus alpha into p minus a into x minus a, this is known quantity. R s is a given function. So, you can find out a to x x minus s r s ds, and third and fourth term involving y s, this actually involves the unknown quantity y. So, therefore, we can write this expression into the form y x equal to f x plus integral a to x k x comma s y s ds, where this f x is equal to this expression, that is alpha plus beta plus alpha p a into x minus a plus the last integral involving r, that is integral a to x x minus s r s ds. And from the previous slide you can see that this entire expression p dot s minus q s multiplied by x minus s and minus p s, these actually give you the targeted kernel of the integral equation, that is k of x comma s, and hence the kernel of the integral equation k x comma s, that is given by x minus s multiplied with p dot s minus q s minus p s. So, this is our target integral equation that we have obtained starting from the given general form of second order ordinary differential equation, which is an initial value problem. We can just have a look at one example. That means, we have to construct the integral equation corresponding to this differential equation d2y dx2 minus sin x dy dx plus e to the power x y is equal to x, where y 0 is given as 1, y dash 0 this is given as minus 1. So, if we compare with our general format for the second order ordinary differential equation, then you can see p x is minus sin x, known function, q x equal to e to the power x, r x equal to x, alpha is equal to 1 and beta this is equal to minus 1. So, quickly if we substitute this expression into this formula, then we can find f x this is equal to 1 plus beta is minus 1. Now, p x is minus sin x, a is 0. So, that means p a is 0. So, no contribution is coming from alpha p a multiplied by x only, because a is 0, plus integral a to x, here a is 0. So, lower limit will be 0 to x, x minus s, r x is x. So, r s will be s ds, and after evaluating this integral you can find 1 minus x, first term x s ds after integration will give you x cube by 2 and minus s square ds from 0 to x will give you minus x cube by 3. So, after simplification this will be equal to x cube by 6, and similarly if you calculate the kernel of this integral equation. So, this will be x minus s multiplied with p dot s, p is minus sin s. So, that means it will be minus cos s, then q is e to the power x. So, that means minus e to the power s minus p s. So, it will be plus sin s. So, this is equal to sin s minus x minus s multiplied with cos s plus e to the power s. Now, here I substituted these expressions into this easily available formula written here, but in terms of the practical problem, when you have to attack, then you have to proceed step by step, but the way out will be this one. Of course, this strategy can be applied to higher order ordinary differential equations also, and here I just consider another example on third order linear differential equation, ordinary differential equation, where initial condition is given, but you have to keep in mind that formulation of a general result, that what will be the resulting Volterra integral equation from a given nth order ordinary differential equation will be a little bit difficult problem, and we can attack that problem using the strategy what we have adopted earlier. If you can recall from the first lecture, where equations, integral equations was constructed from the differential equation, where given equation was of the order second order differential equation. We have started with d2y dx2 equal to phi x, and from there we have calculated dy dx and y in terms of phi and substituted into the original equation in order to get the resulting integral equation. That point I will come later after this example. Now, here another example is d3y dx3 minus d2y dx2 plus dy dx minus y, this is equal to x, where given initial conditions are y0 equal to y dot 0, this is equal to 0, and y double dot 0, this is equal to 1. So, if we proceed in a similar manner, that first of all from the given equation we can write ddx of d2y dx2, that is equal to integral it will be equal to d2y dx2 minus dy dx plus y plus x. Now, we have to integrate this from 0 to x. So, after integration you can find d2y dx2 minus d2y dx2 at x equal to 0, this is 1. So, we can transfer this 1 on the right hand side, and after that we can write integral of this term, that is x, from the range 0 to x. So, it will be x square by 2 plus integral of this expression, that is d2y dx2. So, it will result in y dot x minus 0, because y dot 0 equal to 0, then minus y x plus 0, because y 0 is given here exactly equal to 0, plus integral 0 to x y s ds. Okay. Again you can write the left hand side in terms of ddx of dy dx, and again after integration you can find from here dy dx, this is equal to, no constant term will be adjusted either on the left or the right, because dy dx at x equal to 0 equal to 0. So, this is equal to x plus x cube by 6 plus integral of y dot x, that is equal to y x minus 0 minus integral 0 to x y s ds, and this will be changed to 0 to x 0 to s1 y s ds ds1. Again integrating from 0 to x, you can find y x, this is equal to x square by 2 plus x to the power 4 by 24 plus integral 0 to x y s ds minus integral 0 to x integral 0 to s1 y s ds ds1 plus integral 0 to x integral 0 to S2 integral 0 to S1 y s ds ds1 ds2. Now, in these two last integrals we have to apply generalized replacement formula. So, after applying that formula we can find this will be equal to x square by 2 plus x to the power 4 by 24 plus integral 0 to x y s ds minus integral 0 to x x minus s y s ds plus integral 0 to x x minus s whole square by factorial 2 y s ds. So, ultimately this is equal to the integral equation x square by 2 plus x to the power 4 by 24 plus integral 0 to x 1 minus x minus s plus half of x minus s whole square, this multiplied with y s ds. So, this is actually our resulting integral equation. So, this part x square by 2 plus x to the power 4 by 24, this is equal to your f x, and 1 minus x minus s plus half of s minus 2 whole square, this is actually the kernel of the integral equation. Next, we consider the formulation of integral equation starting from a given nth order ordinary differential equation with n initial condition, those are also prescribed. Now, we consider this equation that dny dxn plus p1x dn minus 1 y dx n minus 1 plus p 2x dn minus 2 y dx n minus 2, proceeding in this way, this will be up to p n minus 1 x dy dx plus p n x y, this is equal to q x, and given initial conditions are y a equal to alpha 0, y dot a equal to alpha 1, y double dot a that is equal to alpha 2. In this way, y n minus 1 a that is equal to alpha n minus 1, and all these functions, that is p r x, where 1 less than equal to r less than equal to x and q x, they are defined and continuous over some closed interval of x starting from the left at a and on the right ending at say a 1. Now, our target is convert this general linear nth order ordinary differential equation where n initial conditions are prescribed, convert it to a Volterra integral equation, and during the process of this transformation you have to be careful about the notation at every steps. Let us start with the assumption. In this case we have to assume dn y dx n, this is equal to u x. Now, this equation possesses a solution. That means, there exists a y which is continuously n times differentiable satisfies this equation, which is a solution of this equation, and therefore, nth derivative of y with respect to s is equal to u x, that is also continuous. So, we can integrate it from the limit a to x in order to get the result d n minus 1 y dx n minus 1 minus this derivative evaluated at a, that means y n minus 1 a, this is equal to alpha n minus 1 and this is equal to integral a to x u s ds, this one. Next, we can transfer this quantity onto the right hand side to get the result d n minus 1 y dx n minus 1, that is equal to integral a to x u s ds plus alpha n minus 1. We call this expression as 1, this as 2. Now, we are going to integrate this second result, that is dny by dx n minus 1 equal to this expression from a to x. Once we integrate, then we can find d n minus 2 y dx n minus 2 equal to the constant evaluated at x equal to 0, that is alpha n minus 2 can be transformed onto the right hand side, and then we will be having integral a to x integral a to s1 u s ds ds1 plus alpha n minus 1 x minus a plus alpha n minus 2. Remember this alpha n minus 2 coming from the left hand side, and applying the formula we can find this is equal to integral a to x x minus s u s ds plus alpha n minus 1 x minus a plus alpha n minus 2, call it 2, sorry it will be 3 because last equation was 2. Now, we integrate not the exactly expression d n minus 2 y dx n minus 2 equal to this one, rather we are integrating the first expression, that is d n minus 2 y by dx n minus 2 equal to double integral this one, such that after introducing the integral sign we can apply the generalized replacement formula. So, using that technique we can find d n minus 3 y dx n minus 3, this will be equal to integral from a to x integral a to s2 integral a to s1 u s ds ds1 ds2. Now, this term, that is alpha n minus 1 x minus a, after integration from a to x will produce x minus a whole square by factorial 2. Here we will find alpha n minus 2 x minus a plus alpha n minus 3, that actually come from the left hand side. So, ultimately this is equal to 1 by factorial 2 integral a to x x minus s this whole square u s ds plus alpha n minus 1 x minus a whole square by 2 plus alpha n minus 2 x minus a plus alpha n minus 3, call it 4. Now, you just have a look at the analogy of this order of the derivative and suffixes appearing here. In case of n minus 2, when order of the derivative is n minus 2, so constant is going up to n minus 2, alpha n minus 1, alpha n minus 2. When it is n minus 3th order derivative is involved, then alpha n minus 1, alpha n minus 2 up to alpha n minus 3, and in this case x minus s whole to the power 1, in this case x minus s whole square. So, that means at the kth step we can find this result, that d n minus k y dx n minus k, that will be equal to, now just try to understand, when 3 is here, that is n minus 3. So, we have 1 by factorial 2 and x minus s whole square. When this is n minus 2, so 2 is here. So, this is only 1 by factorial 1, we can assume this expression as 1 by factorial 1 into x minus s whole to the power 1. So, in case of n minus k, we will be having 1 by factorial k minus 1 integral a to x x minus s whole to the power k minus 1 u s ds, and then we will be having alpha n minus 1 x minus a whole to the power k minus 1, here it will be factorial k minus 1 plus alpha n minus 2 x minus a whole to the power k minus 2 by factorial k minus 2 plus dot dot, last but one term will be plus alpha n minus k plus 1 x minus a, and last one will be alpha n minus k. So, here it was alpha n minus 3 when we have the n minus 3th order derivative of y on the left hand side. Here it was alpha n minus 2 last constant term, where left hand side we have the derivative of n minus 2th order. So, in case of n minus k, last constant will be alpha n minus k. We call this expression as 5. So, proceeding in this way, we can arrive at the second order, first order as well as only y from here by taking k equal to n minus 2, k equal to n minus 1 and finally k equal to n. But here I am writing the result only for dy dx and y only. So, dy dx, this will be equal to 1 by factorial n minus 2 integral a to x x minus s whole to the power n minus 2 u s ds plus alpha n minus 1 x minus a whole to the power n minus 2 by factorial n minus 2 plus alpha n minus 2 x minus a whole to the power n minus 3 by factorial n minus 3 plus dot dot. Proceeding in this way, last but one term will be alpha 2 x minus a plus alpha 1, and again integrating this expression, you can find y x is equal to 1 by factorial n minus 1 integral a to x x minus s whole to the power n minus 1 u s ds plus alpha n minus 1 x minus a whole to the power n minus 1 by factorial n minus 1 plus alpha n minus 2 x minus a whole to the power n minus 2 by factorial n minus 2 plus dot dot plus alpha 2 x minus a whole square by 2 plus alpha 1 x minus a plus alpha 0. This alpha 0 is coming from the left hand side, because y x minus y a is given to be alpha 0. So, this alpha 0 will come on to the right hand side. So, last equation we numbered it as 5. So, this will be 6 and this is 7. So, we have all the expressions starting from y dy dx, d2y dx2 up to dny dxn in terms of u. So, now we are going to substitute all these expressions into the original given ordinary differential equation, this one, and after transferring n minus 1th derivative of y up to y term onto the right hand side. So, that means we are rewriting the equation into this form: dny dxn, this is equal to minus p1x dn minus 1y dx n minus 1 minus p2x d n minus 2y by dx n minus 2 minus dot dot. In this way, ultimately p n minus 1 x dy dx minus p n x y plus q x. So, d n y dx n, this is equal to u x, straightforward. Now, first of all we try to collect the terms which does not involve integral of u's. So, try to understand this point. First of all, you will be having this term q x, then this entire expression in 7, that is alpha n minus 1 x minus a whole to the power n minus 1 by factorial n minus 1 up to alpha 0, this will be multiplied by p n x. Then in expression 6, except the integral, entire expression will be multiplied with p n minus 1, proceeding in this way. Finally, this alpha n minus 1, it will be multiplied with p n minus 1 x. So, what we can do, we can just claim that after collecting this term, we will be having an expression f x plus integral a to x k x comma s u s ds. Now, the task is we have to write what is f x and what is k x comma s. Now, just recall from here, first of all this alpha n minus 1, this alpha n minus 1, it will be multiplied with p n minus 1. So, which gives you ultimately this f x equal to q x minus, just see, alpha 0 will appear only with y x. So, first of all we can write the coefficient of alpha 0. Now, alpha 0 will be multiplied with p n x. So, therefore, it will be minus alpha 0 p n x. Then alpha 1 will comes from only expression of y x and dy dx. So, alpha 1, this x minus a, it will be multiplied with p n, and alpha 1 will be multiplied with p n minus 1. So, therefore, it will be minus alpha 1 then x minus a multiplied with p n x plus p n minus 1 x. Then you can write the coefficient of alpha 2, it will be one expression. Proceeding in this way, last term will be alpha n minus 1, and now just see what is the expressions will be involved. From the first one, this alpha n minus 1 will be multiplied with p 1 x. Then from the second one, alpha n minus 1, this x minus a will be multiplied with p 2 x. Then x minus a whole square by factorial 2, this will be multiplied with p 3 x. So, proceeding in this way, you will be having this p 1 x plus x minus a p 2 x plus x minus a whole square by factorial 2 p 3 x plus dot dot, last term will be x minus a whole to the power n minus 1 by factorial n minus 1 p n x. This is actually expression for f x, and just recall q p n minus 1 up to p n x, all these quantities are known quantities as well as the given quantities. So, this is completely a known function. Now, what will be the structure of the kernel? K x comma s is actually collection of the integrand involved with u s terms. So, from the first one, you will be having just minus p 1 s. Then from the second one, p 2 s multiplied with x minus s, then p 3 s multiplied with this one. So, proceeding in this way, ultimately we will be having this expression, that is minus p 1 x minus p 2 x, it will be multiplied with x minus s minus p 3 x x minus s whole square by factorial 2 minus dot dot, last but one term will be minus p n minus 1 x x minus s whole to the power n minus 2 by factorial n minus 2 minus p n x multiplied with x minus s whole to the power n minus 1 by factorial n minus 1, and we can write this entire expression into a compact form using the summation notation, that is minus sigma r running from 1 to n x minus s whole to the power r minus 1 divided by factorial r minus 1 multiplied with p r x. So, if we start substituting r equal to 1, 2, 3 up to n, so we will be having this entire expression. So, that means a general nth order linear differential equation can be converted into Volterra integral equation of second kind by this method. Now, the most crucial question is that in one method we have obtained the differential equation in terms of the unknown function y, that is with the first approach, and in the second approach we obtained the integral equation in terms of the unknown function u, where u is the nth derivative of y. So, what is the relation between these three, that is the given ordinary differential equation, integral equation in terms of the unknown variable involved with the ordinary differential equation, and integral equation in terms of the unknown function which we are introducing in terms of the formula dn y dxn equal to ux. Answer to this question is that if phi x is a solution of the given ordinary differential equation, then you can verify phi x will be solution of the integral equation what we have written in terms of y, and nth derivative of this phi x will be solution of the integral equation what we have written in terms of u. So, just have a quick look to this example, then you can clearly understand this idea. Consider this equation d2y dx2 minus y, this is equal to x with the given conditions y0 equal to 2 and y dot 0 this is equal to 1. So, using the first approach, integrating this equation, you can write dy dx this is equal to 1 plus integral 0 to x ys ds plus x square by 2, this one is coming from y dot 0, and further integrating you can find y x this is equal to 2 plus x plus x cube by 6 plus it will be actually integral 0 to x, then integral 0 to s1 y s ds ds1, and after using the replacement formula you will be having 0 to x x minus s y s ds. So, this is integral equation in terms of unknown function y, but if you use this notation d2y dx2 equal to ux, then from here integrating from 0 to x we can find dy dx this is equal to 1 plus integral 0 to x us ds, and again by integrating this expression we can find y equal to 2 plus x plus again using the replacement formula it will be x minus s us ds. So, y d2y dx2 equal to ux, y is this one. So, clearly from the given equation you can understand the required integral equation is ux equal to y plus this one. So, that means 2 plus 2x plus integral 0 to x x minus s us ds. So, call it as 1 and call it as 2. So, this is the integral equation in terms of the unknown function y, and this is the integral equation in terms of the ux where u is the second derivative of y, and for the given ordinary differential equation if you solve it then you can find solution will be y x equal to 2 e to the power x minus x, and therefore, solution of Volterra integral equation, in short we can write this i.e. 1 is 2 e to the power x minus x, and solution of the Volterra integral equation 2, that is in terms of u what we have written, that will be the second derivative of this function, that is 2 e to the power x. You can verify these are the solutions of these two problems. So, this lecture we can stop at here. Just for a quick recapitulation, that we have started with a second order ordinary differential equation initial value problem, where p x q x r x is given. Then using the generalized replacement formula and integrating the given equation both side twice, we obtained the general format for the integral equation in terms of y. This is a Volterra integral equation of second kind, where this f x given by this formula and kernel is given by this one. Then we have considered one example where p x is minus sin x, q x is e to the power x, and right hand side function is x, and this technique can be adopted for third or fourth order equation, but of course, it is not possible to extend this idea, that it will be little bit difficult to arrange these terms appearing after integration to write down the Volterra integral equation in terms of for the nth order ordinary differential equation. For those case, we have to assume dny dxn equal to ux, and then using the successive steps you can find n minus 1th derivative of y in terms of u, n minus 2th derivative of y in terms of u, and in general n minus kth derivative of y in terms of u. Finally, you will be arriving at this integral equation, and then I have explained here the relation between the two methods, that means solution of the original differential equation will be solution of the integral equation if it is written in terms of the unknown function involved with the differential equation, and its nth derivative, in this case we are considering second order differential equation. So, second order derivative of solution of the given equation will be solution of the Volterra integral equation written in terms of u. So, I stop for this lecture at this point. Thank you.